All right, so welcome to this stream today. Today I'm gonna try to implement a compiler out of our little language, and in particular compile to WebAssembly. So let's see if we can make that happen. Let me share my screen and let's get started. So one thing I wanted to just mention is that last time we tried to get the type checker to work and it didn't work. At the end, there was a bug I couldn't find, so I stopped the stream after some time. After that, I took a break and then I looked at it again, and then I just changed it to use the union map, find union map data structure. So we used the union find algorithm to make the equivalence classes for the type variables, but there is a union find map which can also associate a value with those guys. And once I changed it to that, then everything worked. So that's fine. The other thing I did is that I wrote a small program just to have something to try out. And I wrote this little program in our language that counts the number of primes between these two numbers. So let's try to run that. Yep. And see how many primes there are in that range. There you go. So there are 2,360 primes, it seems, in that area, in that range, and it took 0.47 seconds to evaluate that program using the C++ byte runner. So one thing I wanted to show you is that we can also try to run it as Java, because Flow can compile to Java, and it's as simple as invoking the compiler and just saying that you want a jar file out. There you go. So then it'll compile it to Java files and then invoke the Java compiler to construct the Java file. And then we can try to run the same program now using the Java runtime. .jar and see if that's faster or slower or whatever. And there you go. It's twice as fast. So Java is a pretty decent target for this thing. Now, what I want to try to do is that I want to take, and this is the interpreter we wrote a couple of streams ago that ran there. So this is an interpreted evaluation of that program. And then we took the interpreter and compiled it to Java and run it there, and that's how fast it is. All right, so what we want to try is that, what if we compile the program instead of interpreting it? Can we get a speed up? Can we get it to run faster? So the way I want to do that is to implement basically a compiler. And so WebAssembly, you can target that in a number of different ways. One thing, at the lowest level, you can write out the raw bytes. WebAssembly is a binary format. I don't think many do that. Above that, there is a WASM text format. It's like a list of instructions that's like an assembly language, stack-based language that you can write out and then compile that to the binary file. You can also use binary-yen. I don't know how to pronounce it. It's the backend that's used by many languages that produce JavaScript, and it's basically the same as the text format, except it's S expressions. So it's a little bit higher level than the text format. And as you know, the higher level you target, the easier it is to write the compiler. So today I'm going to cheat. I'm going to target something called Grain, which is a functional language that compiles to WebAssembly. So it's this thing here. They have a website. It's like an ML language, a functional language that compiles to WebAssembly. And if we look at this language, it's a pretty, since it's a functional language, it's a good fit because it basically has more or less the same semantics as the toy language we made. So it has this simple syntax. They use let syntax, and they have the different data types. You have if statements, functions. You declare them using this syntax instead of the syntax we chose. So it's pretty similar. So let's go and try to implement this. And the way to do that is just to say, okay, what is a compiler? A compiler takes our typed expression and produces a program as a string. That's it. This is something we already have, except that we don't have it for the language we need. If you remember last time, we have these pretty printers that can print out the program easily. So this is a good start. Let's just copy this guy and see. This one took a type environment, and I guess it's because we had the type variables, but we instantiated those here. So in this T expression, all of the types are instantiated, so we do not need that type environment for our guy. So what we're going to do is that we're going to run the type checker first and type our program, and then once we have that, we're going to call the compile to grain function on that expression like that. And then we're just going to save that in a file. For now, I'm just going to hard code the name. And then after that, we can compile that file with the grain compiler, and then we'll get a JavaScript WebAssembly out, and we can run that. Okay, so import the grain. And here, we do not need the type environment. So, all right, we got to figure out what the syntax is for everything in this language. And what we can do at first is we can just say, let's just do it with this guy, just to have something that compiles and runs. T expression, is that the name? Yeah. Pretty T expression. Yeah, we got to rename this guy to this, and we do not want the environment, so we can just do it like this. Compile to grain, and we don't, the PT, the type things, we do not need that. So just get rid of those. And there are still some types here. Let's just get rid of those guys. Okie dokie. So let's try to run this program and see what we get out of it. And we can turn off the evaluation and then just run this guy. So it's this guy. There is a print here, the result of the type checking. We can turn that off. We don't need that. All right, so now it should have produced a program here in this file. And indeed it has. So we can start to fix this up now to make it use the grain syntax. So let's just start and do that for each construct. Array values, grain it has lists as the primary, these are single linked lists and they do not support indexing, but I happen to know that they do have arrays, and you use this strange syntax here to get arrays. That's easy peasy. You just use like this, then you have arrays. Lambdas, they write the arguments in a parenthesis and then an arrow. That's how they do that. Let bindings, they have the keyword let in front and then the body. What else? Variables, that's the same thing. If conditions, that's the same thing. Calls, they're the same thing. Array constructor, that's the same thing as this guy. And sequence, that's this guy. We don't want the type thing. A sequence, I think they have the same syntax for sequence, but I must admit, I don't know. I just found this language today, so I'm not really a grain expert. So here you go. All right, so looks probably like grain, I don't know, but we can see a bunch of problems. So here, this guy is should be a binary operator. So all our operators, they are printed out as calls now, but that's obviously wrong. All right, so we'll fix that. So here in the call, we gotta check if the, so basically similar to this guy, we also had that in the type checker somewhere where we handle all the built-ins. As far as I remember, yeah, we have this guy, something like this. I think that's pretty similar. So if the if the function is a var and it's a built-in, okay, so we'll see built-in. So we'll say compile built-in to grain, and then we'll say the ID and then the args. And let's just make it so that this can return the empty string. Okay, so we can just do it like this. I think let's just do it like this and say if this is the empty string, then we should use the call. Okie dokie. And if if built-in is the empty string, then we do this thing. Otherwise, we have the result from this guy. Okay. So we have to define this guy, and it takes an ID and the arguments, and should return a string. If the ID is equal to, well, then we have a binary. Okay, we can do it like this because I think this is going to be very much the same for a lot of them. So we'll compile the first arguments in a binary plus the ID plus this guy, number one. And then just because we don't want to have any precedence problems, we're just going to do this. So, okay, we can say contains a list of all of these guys. So it's like or and plus minus multiplication, division, all the comparisons. I think that's a good start. And if we have that guy, then we'll do that. Okay, so let's just see if this works. What did I do wrong? I guess I need the end of the array. Expected semicolon plus. Okay, so let's try that and see if that improves our program. Yeah, we do have some binary operators now. That's nice. What else is missing? If we look at this program. Hey, maybe it's valid syntax now. Who knows? Let's just try to compile it with this compiler. So the grain compiler is here, and we call it program grain, like that. It's doing something. Yeah, I don't know. Maybe this compiler is really slow. Who knows? Or maybe we've found some bug in it. Hard to say. Well, I guess while it's compiling, we can try to look at, see if we can figure out what the syntax is for sequence. If they have braces like that, I guess, yeah, it seems like they do have these guys. I was looking at the documentation to try to find a language reference, but I couldn't find it. So I was like, it's a new, I guess it's an immature language somehow. Still working. I think we caught some bug, don't you think? It seems strange that it should take so long to compile this small program. Well, here it is their code, and I'm guessing we can find out what the language is. Lexer, here's a parser, parse tree. Dup, what is dup? I don't know what dup is.
I don't have an answer for
My Alexa just started to complain. All right, so they have something here: statement expressions, operators, lambdas, assignments, patterns, tuples, types. Okay, so they have left brace record patterns. Okay, is that what it is? Or maybe they have record patterns, import shape, data constructors, simple expression, record expressions. So maybe they don't have braces like we do. Okay, they have a black expression. Okay, they do have block expressions here. So a block body, what is a block body? Oops. Block body, let expression or expression. Okay, so it should be the same, I think. All right, unbound value check prime. Finally, okay, it says we need to add the rec keyword for recursive functions. Damn, that was a slow compiler. That's correct. My program is indeed recursive. So let me just add the let rec thing manually and see if we can get it to compile now with that thing. And while it's doing that, then let's try to figure out how to do the, we need to add a let, a rec here in case it's recursive. All right, so we'll just see contains var. So what we're going to do is that we're going to make a function that says, is this ID reference somewhere inside this expression? And if it is, then it's then we can use that to check whether it's recursive. All right, so we have all our guys here. Contains values, no, exists, I guess, values. Rec, we'll do the rec trick. Like this. Lambda, it's just a reg on the body. Provided the argument is not one of those names. So contains args ID. If it does that, then it's not contains and, because if it has the same name, it's a shadowing, right? Technically, I guess. And it's the same thing here. If, okay, we have ID collision here, so let's just call it let ID. If ID is this guy, then there's no problem. I guess then it's false, else this is, so it's the same thing as before. We'll just say ID is different from ID and recursive on the value, recursive on the body. I believe that's correct. So here, if we have a, if it is this guy, then we found it. Rec cont or rec then. So I guess it's or up here with these guys. If it's just referenced in one of them, it's an or. Humans are not made for logic. We don't know how it works. Our brains just shut down when it's basically a negation. I don't know if any of you have tried that ever. Make a mistake. Exists rec like that. Exists values rec like that. And the same thing here. Exists values rec like that. All right. So the thing is, if our let binding contains this guy, if the value contains the ID, then it's recursive. All right. Okay, so we can say, we can add this as a string. Like that. Okay, we can add a space here. I believe that should do. In the meantime, did it complete? What did it say? Maximal call stack size exceeded. Okay, so our program is too big. It's doing too much work, crazy stuff. All right, but since this is pretty easy to read, we'll just reduce it and just see if we can get it to run with 100. I guess they don't have tail call elimination if this call stack is succeeded, unless of course we have a bug. It finished, it didn't do anything. I guess they don't print the result. So let's just say we print the result at the end. Let's try that. Expression has type void. All right. I put the parentheses the wrong place, like that. Damn, it's a slow compiler. This is a tiny program, 50 lines of code. 25. Looks good to me. All right. So what we should do, I guess, is we should just change our program to have that print here, and then also compile that to their print. So if we run our program again here, pflow, this guy, error unknown ID, println. Yeah, our type checker doesn't know about println. So what is println? It's a function that takes one argument and then it's a type variable, right? Yeah, I guess it is. It's polymorphic. How do I make a type variable? It's like this guy. Okay. And it returns, yeah, I guess a bool is fine. Expected one of what did I do wrong? Okay, let's try again. Oops, that was the wrong one. Let's run our compiler. There you go. So now we got this code and it did add rec here. That's fine. And here as well. That's fine. And we have the println here. So this looks strange. That's obviously probably not the, well, anyways, it's the wrong name. So let's fix the name of that guy. I guess it's a built-in. So else if ID equals println, else, then we're gonna say print. That's what they call it. And we can just do it like this. That should be fine. Okay. And then we had a problem that our program was running too much. It didn't want to do that many. I forgot how many I want. 200. Let's just do 200. Okay. That was our compiler. And let's check the program. It has a print. It looks about right. So let's try that compiler again to see if it works. $46. It worked. So that's it. So if we look at it now, there is a WebAssembly file here. That's our program. And I can even run that thing with WASM, and it runs. Okay, so far so good. So that's pretty nice. We want to see, the problem is we can't run with big programs because it has this Stag Overflow problem, which is pretty bad, huh? I don't know. Let's see if it can do 20,000. We need to have some, it needs to run a little bit so we can see how fast it is, right? I don't know if 20,000 is too much. Yeah, it's too much. What is the stack size? Who knows? This is why you need tail calls in your language. This is just crazy. I guess we could attempt to compile recursive calls to while statements, but I don't think it's worth it today. This is too small a number, I think, before we can measure anything in terms of speed, but we can try. I know that they have this stuff I've prepared for how to do time in grain. So let me just add that stuff here. And then you have your code, and then it can print how long it took, like that. So let's try to add that and see how fast it runs now with this runtime, so to say. Oh, I think I forgot to, no, yeah, that's fine. 42 milliseconds, I believe. Is that correct? I don't know what the unit is. How many zeros are here? 1, 2, 3, 9. I don't know. Monotonic time. Could it be 42 milliseconds? It was pretty quick, wasn't it? When you run it. Whoops. WASM program.gr. WASM. Yeah, 40 sounds like 42 milliseconds, maybe. I don't know. What do you think? Hard to say. But it's such a small number now that I guess our program is also our interpreter is also very fast. So let's just try our thing directly, our interpreter, with the same, 0 seconds. So we can't really measure it with this program. We gotta have a program that doesn't have tail recursion. But the thing is, in the lambda calculus, you can't do any loops without tail recursion, right? So it's like, that's the only way you to iterate. So I guess if Grain doesn't support tail recursion, we would have to do the while thing. I can sketch out how that would work. So basically, I don't want to do it. I don't think it's worth it. But what you can do is that if you have foo a by, let's do the factorial example. We have the fact in here. So basically this function here, no, that's not tail recursive. All right, let's do a tail recursive function. Count. Count, the syntax is this. It's like this. If n is less than 0, then we're done. Let's say that. Otherwise, we're going to count n minus 1. That's a tail recursive function. So the way to convert that into a while loop is that you take this body, and then you say basically while true, like this, and put in the body here, and then where you have the tail call here, whoops, where you don't have a tail call, you break. And where you have a tail call, you use assignment to update the variable. So you cannot do this in the language itself, but in the host language, when you compile it, if they have assignment, this is updating, you would have to do that. I think they do have that in their, they call it mute or something like that. So we would, so basically the code would be like this, I think in Grain, something like this. So you can do that. It's not that hard to do that conversion when you're making the compiler, that instead of producing this code, you produce this code instead. But I don't think it's worthwhile to do it. So that is, I think, all I wanted to show you today. So doing a basic compiler is pretty easy if you target a high-level language that has the same structure as your own. Obviously, we could target other languages. An obvious one would be JavaScript. JavaScript is also a pretty high-level language, but there is one big difference compared to our language, is that it's a statement-based language, right? So if we wanted to compile to JavaScript, it wouldn't work, because in our language, we can say something like, if A equals B, B different from 0. So we can have a let binding anywhere, right? You can do stuff like this. That's fine in our language. That's not a problem. But you can't do that in JavaScript. You can't have variables inside the expression places. So to compile to JavaScript, you have to take this guy and then move them out, so to say. You have to lift these guys out before the if statement like this. You have to do this lifting, so there's a transformation. And also, you have to add returns, because in our language, we don't have to return anything. We just, the result of a function is the last element in a sequence or in your expression. But in JavaScript, you have to add returns for everything you do. So to compile to JavaScript, it's not that hard, but you just have to track and convert to a statement-based language. So, all right. Any questions from anyone today? A little bit disappointing they don't have tail call, so we could see if it was faster, but yeah. We could file a bug report, I guess, to those guys. Well, it doesn't sound like there are any questions. So in that case, Pretty simple, easy one today. Hope you enjoyed. And then there is something in the chat. There's a question. Okay, so Daniel, what's your question? We can, in theory, convert Java to WebAssembly. Sure. There are many languages that compile to JavaScript, to WebAssembly these days. The problem with Java is the same as JavaScript. It's also a statement-based language. So, you know, I could do it if you want me to do it at next time. Maybe I could compile to an expression-based language, no, to a statement-based language. It's not that hard, but I don't think it's that interesting. So, yeah, surely that's possible. All right. Well, okay. So that's it, guys. Have a nice weekend and see you next time. Bye-bye.
Bye.